Learn loss functions and use them in Python models. By the end, you will know how mean-squared error and binary cross-entropy work. You will see simple Python examples that compute both and compare models. You will run a single gradient step to reduce mean-squared error and learn which loss to pick for regression or classification. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. Loss functions pick what a model should optimize. Mean-squared error, which measures the average squared gap between predictions and true values, focuses on numeric accuracy. Binary cross-entropy, which measures how well predicted probabilities match binary labels, focuses on calibrated probabilities. Expect a trade-off. Mean-squared error is sensitive to outliers, but simple and fast, while cross-entropy gives better probability learning, but needs stable probabilities and can suffer if values hit exact 0 or 1. Intuitively, mean-squared error punishes big misses more than small ones. Cross-entropy punishes confident but wrong probabilities much more than unsure guesses. Use mean-squared error for direct numeric prediction and cross-entropy when your model must output probabilities. Both are easy to compute in Python on small data, but both need careful scaling and numerical guards on probabilities. We will work with the same tiny example dataset throughout, house size to house price, with a derived binary label for whether price is above a threshold. First, we will compute a simple mean-squared error for toy predictions. This snippet computes mean-squared error for simple predictions and prints it. This snippet shows how to take a vector of true prices and a vector of predicted prices, subtract them, square the differences, average those squares, and print the resulting number. It uses the same house size and price example so you can see how prediction errors translate into the loss value. If you change the scale of prices, the mean-squared error moves dramatically. So you learn why normalizing inputs or comparing root mean-squared error sometimes helps when you want human-readable units. Next, we will compute binary cross-entropy on predicted probabilities. This snippet computes average binary cross-entropy from labels and predicted probabilities. This snippet takes the binary labels derived from price threshold and a vector of model probabilities, then computes the negative log probability of the true class and averages across examples to get the loss. It highlights how a probability near 1 for the correct class gives a small loss, and how a probability near 0 for the correct class gives a huge loss. So you see why probability calibration matters. If you adjust the way probabilities are produced, for example, adding a temperature or smoothing, the cross-entropy changes and you get different model behavior. Next, we will compare two models using the regression loss. This snippet compares two models by MSE and selects the lower loss one. This snippet evaluates mean-squared error for each model on the same example set, and then chooses the model with the smaller average squared error, demonstrating a simple model selection rule. It keeps the same house data, so you can directly compare how a linear model and a slightly shifted prediction perform. This comparison illustrates a practical pattern. For regression tasks, use mean-squared error to rank models, but remember that it favors lower variance and can reward bias if outliers are downweighted. Next, we will stabilize cross-entropy by guarding extreme probabilities. This snippet stabilizes binary cross-entropy by clipping extreme probabilities before the log. This snippet shows that when predicted probabilities are exactly 0 or 1, the logarithm becomes numerically unstable. So it first clips probabilities into a safe range, and then computes the average negative log likelihood. You will see how the clipping threshold affects the loss. A very small clip keeps maximum fidelity, but risks instability, while a larger clip makes the loss more forgiving and avoids infinite values. Choosing the clip value trades numerical safety for strict punishment of overconfident mistakes. Next, we will take one gradient step to reduce the regression loss. This snippet performs one gradient step to reduce mean-squared error in a one-dimensional linear model. This snippet computes the prediction error on the house dataset, calculates the derivative of the loss with respect to the slope and intercept, and then updates those parameters using a learning rate to make the next prediction slightly better. The snippet highlights the role of the learning rate as the adjustable parameter. A larger learning rate moves parameters faster but can overshoot and increase loss, while a smaller rate makes slow, stable progress. Seeing one step helps you connect the loss number to parameter updates. Quick recap. Mean squared error measures average squared numeric error and suits regression. Binary cross-entropy measures average negative log probability and suits probability outputs for classification. One caveat is numerical stability, so clip probabilities and control learning rates. Next step, run multiple gradient steps while sweeping the learning rate and plot loss curves to see convergence and sensitivity. That single experiment will teach you how clip values and learning rates change training dynamics. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.